second lecture, I just want to focus on the shock breakout, light curves, cooling, what we actually see when we're looking at the transients. So I have all these diagnostics, but I want to just talk about the physics that we're worried about and what we're doing for the modeling for these light curves, and what are the hints and constraints that we're getting on the supernova, the explosion mechanism, and the progenitors from these objects. And the reason why we want to do this is because we do have a lot of data from these transients. So I couldn't find something that kept on going, but this is even going out into 2015. The number of supernova detected, from the 1880s. I realize, Tony can remember those times, when there's only a couple. You had to wait several years for a supernova, and now we're getting a large number of supernova observations. And so the data is there's an immense amount of data, but what you'll see is there's a lot of work for us to do on the theoretical modeling to actually analyze that data and place some constraints on what we're observing. So that's what I'm going to go over in this talk. There was a nice study done where they took, so just to give you the first, this is not even the full uncertainties in our modeling. These light curve plots, these are all light curves, different bands. They're studying the same toy type 1a model, where they said, we're going to make a type 1a with a simple explosion energy. We're all going to have the same velocity profile of the ejecta. We're going to have the only energy source is nickel 56 decay. So they agreed on everything that they're doing. We're going to use these atomic capacities. But the difference was how they implemented the capacities and how they did the radiation transport. And so the schemes used here go everywhere from flux limit diffusion, moment methods, different moment methods, to Monte Carlo transport and discrete ordinate like SN or spherical harmonic methods to try to solve these. So there's a broad range of mechanisms. And depending on which band you look at, they're doing okay. They're within 10–20% of each other. Because these are done in magnitudes, so log plots divide by 2.5 to get the exact log. So that you can see there's some ranges, but there's some features that are just crazy. Some of them have double peak features, some do not. It's the same explosion. Everything is the same, and the light curves, if you look at some of these, like, I don't know if I could point this. The light curve here, some of them are doing these weird double peak explosions. That's where we're at right now. Is the details of your modeling can make a very big difference in the result. And the story that I like to say, because it's one where I was clearly being an idiot. We had a supernova go off. I was so convinced it was really bright in the X-rays. It had this long X-ray light curve. I was convinced this had to be a pair instability supernova. This was dead on, no way to explain it other than pair stable supernova. We did a whole slew of pair instability supernova explosions, matched the light curve. We published the paper, and then Dan Casing comes out, and he does it with a 10 solar mass star with a shell on the outside. So he just is powering it with shell interaction. We were doing shell interactions too, but just a slightly different features in the shell, and he could explain the same thing that we argued had to be a 200 solar mass star. He got it with a 10 solar mass star. If you look at the IMF, the 10 solar mass star is probably the right answer. So Dan got it right, I got it wrong. That's where we were at. But we were off by 25 on what we were fitting, the mass of the star that we were fitting to this light curve. So this kind of thing is one of the difficulties we're having. And the reason we have these difficulties is that the uncertainties are not just, it's not even just that. We don't really know the initial conditions. So it's not just the ejecta mass and the total energy. It's how do you distribute that ejecta mass? So how much mass is going at this velocity versus this velocity? That makes a difference. And we see this in kilonova. It can make, you can analyze a kilonova and get an order of magnitude difference in the total mass ejecta just by playing with the velocity distribution of the ejecta. Then you have to argue what are the dominant power sources. So it used to be that we thought if it's a type 2, it's mostly shock heating that powers the light curve. if it's a 1BC or 1A, it's mostly radioactive decay. What we've learned is that there's a lot of ways you can add extra power. So is there a long-lived energy source like a magnetar in the center? The shock heating now is the realization with the supernova transient community is they had underestimated the role of shock heating, and I'll show you some of the evidence. But the reason why instruments like the Ultrasat satellite, the UVEX satellite, this Ultraviolet Explorer, are being developed, a lot of X-ray satellites are being developed, is realization that shock heating is playing a dominant role not only in just the type 2s, but also in the 1BCs as well. And if we don't understand that, we're we could be really misinterpreting what we're seeing in the light curves. So this is the thing that's facing the light curve calculations. But even with all this struggles, I think the light curves are telling us something. And this is a plot by Dan Purley where he was looking at the ZTF, so the Zwicky Transient Factory data. And he was just putting what are the how many of different types of supernova do I get? So you look in the big plot, that's how many 1As have they seen with ZTF? How many core collapse have they seen? So the green are the core collapse. Now let's look at the core collapse. How many are hydrogen? So how many are type 1 supernova? Well, the bulk, almost 3/4 have hydrogen. About a little over a quarter do not have hydrogen. So that's, we're going through, this is the ones with, most of these are hydrogen, some are hydrogen poor. And then if you go down to the ones that are hydrogen poor, most of them, over half, are 1BCs. But there's a set of weird ones. There's quite a few of these superluminous supernova, so they're much brighter than normal supernova. And there's two kind of dominant mechanisms for what power those light curves. One is there's a long-lived engine. The magnetar people love that. That's what they're arguing it is. The other is it's shock heating. And if you talk to the extremes are, there's groups that think all of them are magnetars. Manos Chatsopoulos at LSU would argue almost all of them are shock heating. But that tells you what you're looking at. But there is a subclass. It's 20% of all hydrogen-poor supernova in the ZTF sample are broad line. So they have fast features to them. Those, a large fraction, about half of those, are associated with gamma ray bursts. So because they're associated with gamma ray bursts, we think those are jet-driven. Probably the other half that aren't associated with the GRB are also jet-driven. So that's the kind of hint that I'm seeing is 20%, it looks like 20% of the hydrogen-poor supernova are jet-driven. We do not see any evidence of jets in the helium. These are all 1Cs, though. So we don't see them. If there's a helium envelope on top, we do not see jet-driven supernova. We don't see any evidence of a jet-driven with a hydrogen envelope. We see it only with helium-poor, hydrogen-poor explosions. A large fraction of them are GRBs. That is telling us something. And it's telling us something about the progenitor. Something about the progenitor means I have to get rid of the helium envelope to make something that's rapidly rotating enough to make this jet. And so I would argue it's that. So it's 20% of roughly 25% of all core collapse supernova. So roughly 5% of supernova are, I would argue, are probably jet-driven. And you can change that number, depending on the analysis. But that's what we're seeing. We're also seeing that those supernova tend to be in lower metallicity conditions. So there's hints on what we need to learn about the progenitor just from data like this. And that's going, I think, in the long run, going to help us with understanding the progenitors and then the explosion mechanisms. So I think even with all the difficulties we're having with modeling the light curves, the light curve data is telling us something. And so there's two main arguments to why we're only seeing jet-driven and there's many. We have papers reviewing all the different ways of doing this. But the arguments are something like either you have this kind of homogeneous mixing, this extensive mixing, only happens if the star is rotating really rapidly. And so you burn all the helium when you're rotating rapidly, or it's actually it's a binary interaction that's making the spinning, and you need really, really tight binaries such that even helium star binaries are not compact enough. Either case, that means we need to understand our stellar progenitors better, but it's telling us something about stellar evolution. So, I mean, I think a lot of the rest of my talk will be how hard it is to make these calculations, but the fact of the matter is there's data there that's already giving us good clues on what's going on with the explosion mechanism. There's lots of ways of going about how do we understand things. The problem, I made the mistake of deciding I thought the engine was too hard, so I was going to go and work with observers and work, I thought I could model, anybody could model supernova light curves, so I'd do something easy. And the problem with that field, and this happens with every single event I've studied with the observers, is they find an object and they say, we have this object. We want to submit the paper in 3 weeks. So all of our models are, what can we accomplish in 3 weeks? So we don't do as many of these kind of detailed studies of what are what are the trends and stuff like this. We need to do more of those, but I will tell you, most of the people that are doing the modeling are kept awake 24/7, just trying to keep these darn observers in. I mean, I remember with the GW 170817, I had just given a talk saying, we may get some neutron star merger detections, but it'll be a while before we get electromagnetic. The next day, I'm driving home from that meeting. It was in Washington, the Institute for Nuclear. I'm driving home. So a day after I said, we have years to model electromagnetic signals well. A day later, I get an email from someone on the LIGO team. He wasn't supposed to send me this, saying, we got one. And I said, oh, that's fine. And then he sent me another text saying, and we got an electromagnetic signal. And so then I told him it's not April 1st, and I kept on driving. And 5 days later, the observers wrote me and said, you have 2 weeks to model this thing. So that's our kind of, we're trying to do this. I decided, okay, I have a student. I'm going to let them just do a parameter study. Let them explode things, play with the nickel mass, the nickel distribution, the velocity. So these are a set of models. On the left, it's a set of models where we played with where is the nickel distributed. So we took some of it, the nickel is in the core for the core collapse model. Some of it, we spread it out. And that will change, that changes the rise time. So you'll see it. The ones that have the nickels mixed out is like the red curve where the nickel is mixed out all the way to the edge. That'll make a brighter light curve sooner. If the nickel is more centrally located, that's the purple curve. That will make it so there's a delay in when you see the light curve. So the light curve peaking just from this kind of emission depends on that. So you can play around with that. You can also play around with the velocity. So in this, this right plot, the thing to bear in mind is the main plot is a log plot. So it's log luminosity versus time. The little insets are if I don't do a log plot. And that's probably more what you're used to seeing when you see light curves as non-log. If I change the velocity, that also changes when do you see it. This is well known. We know the basic trends that you would see. And this gives us a set of light curves. It gives us a rise time and a fall off time. And we can use that to compare to existing supernova light curves. What none of these models fit was data that we saw with the SWIFT satellite looking at supernova. And that is that they're ultraviolet bright, not just at shock, what people thought of as shock breakout, but for long times. For the first 10 days, they are bright in the ultraviolet. There's a whole set of them. So the points in this plot, these are different models where we have points that are observations from SWIFT. The light curves on the left panel here, I really suck at this point. The left panel here are light curves where I don't add any shock heating. These are the light curves here are where I've added shock heating for these. These are all 1BC supernova, so no hydrogen in the envelope. So if I add extra shock heating, I can match the ultraviolet. And so that is either assuming that I have this asymmetric explosion going through an asymmetric star, and there's lots of internal shock heating, or in the circumstellar medium, there is shock heating that we have to account for. And either one can help contribute to this. We see the same thing in type 2, where there's shock heating there too. So we need to match the data. We're needing to add extra shock heating to the models. So we need that for both. This was one of the big realizations in the supernova observer community, that the simple models with just this playing with the nickel, playing with the velocity, playing with the mass are insufficient to explain the light curves. So people started to do this. We're getting more and more data. We had some discussion earlier this week about what are the durations of the shock breakout signals. So we have 2008D, that was our first one. It went up and down in a few hundred seconds. It was really sharp, and that fit the little simple analytic spherical cow model perfectly, and it was great. And they said, oh yeah, we can measure the radius of the star. Everything's happy. It is that purple line in this plot on the right. It's the purple line. This is log time, so it's giving you an idea of the duration of the shock breakout and the luminosity. The luminosity is all over the place, so this is log luminosity. It's many orders of magnitude. In defense of that, some of these are, I think, are actually low luminosity GRBs. So let's not, even if we ignore those, we still get quite a bit of variation. But this is the kind of variation in the what was traditionally called the shock breakout signal. The community is trying to change that name, because it's not really shock breakout, it's shock interactions. It happens in the wind, it happens, so it's something that's a more continuous event. And if you really want to get the physics right, you have to include all of that. And what you're seeing here, when you get durations that are over 10 to the 5 seconds long, you need to have something that is driving a lot more shock interactions when you're studying this. So these are all, this is from a paper by Isles Ferris. I don't know how to pronounce his last name, Rob's paper. We then could fit the observations for there was an Einstein peak, Einstein satellite detection that we were trying to model, where at about it had just a huge bright X-ray signal and then broke off, and they wanted to prove that it was a GRB, and I think it probably did have a weak jet, so it may have been a jet-driven explosion, but we could fit that signal with either a jet-like structure or that had a fairly modest Lorentz factor, 5-10 peak of the Lorentz factor, or you could match it with a stellar explosion with a Lorentz factor as a factor of 2. And you say, oh, well, we don't produce Lorentz factor as a factor of 2 in our explosion energies. That's true, but when the supernova shock breaks out of the star, it will accelerate and it will get to high Lorentz factors. And so you could explain a high Lorentz factor with either a jet or a shock breakout model. In fact, the original, I don't know how many people know, the original gamma ray burst engine model was actually not a jet. It was actually the acceleration of a shock outside as it went down the steep density profile of a star. So it was by Sterling Colgate in the early, was it 1969, 1979, 1979. You can get these high Lorentz factors even if you don't have, in the shock breakout, even if you don't have a jet to produce it. But these are the kinds of things that we're studying. So we have these shock breakout signals. They are longer duration than you would expect with a simple analytic model, but there's lots of features like what David Vertenyon were talking about that include it. It can change it. One of the others is, one of the things that we have to also include is the shock interactions. And shock, the circumstellar medium is just messy. It's, if you look at, there's, Dave Arnett was pushing that he'd get explosive burning in the shells that can drive outflows from the star. You can have opacity inversions that drive outflows from the star. You can have common envelope events that eject shells of material. And the shells are not clean, right? So they're not this nice spherical shell, although when we model them as theorists, we immediately do that to make them easier. This physics is messy, and we will probably have to include all these shock interactions to study this physics. Okay, so we have that feature that we're doing. How does that affect the light curve more than just the shock breakout? Well, it also affects the light curve in long duration. So these are actually the same study where I was playing with the nickel distribution, the nickel velocity, the velocities, the mass, all of this. We can also play with the amount of shock heating. So these are some models where we just varied how the shock heating happened. Well, these curves don't look all that different than the curves when I'm nickel powered. So it's not easy to distinguish these. And in fact, you can, it depends on how you implement the shock heating, but you can get a wide range of results. You can do it if you do a simple model where you just say it's a shell and it's a nice spherical shell and it's spherical blast wave, the shock heating will be more dramatic and you'll see a sudden rise and sudden decay. But if the shock heating is what we think it's going to be, you're going to produce something that has a rise and decay. And so then you can start saying, well, how does that compare to the data the same way that the nickel-powered light curves are? And here's a plot of it's a measure of the rise time versus the decay time. So you have the light curve, it goes up, it goes down. There's a set of data that were produced that looked at 1C supernova, broadline 1C supernova, and the pink and red triangles and stars or pluses are those data. So they have a fairly, they have a range of rise times that can go from a rise time of 5 days to a rise time of almost 20 days. So the rise time can vary for these 1Cs. But the key feature of this is the fall time, the fall off time for those models are all pretty short. So if it rises in 5 days, it's usually the fall off is in 10 days. If the rise is more like 15 days, the fall off is 20 days. But they go up and they come back down. That's actually harder to produce with nickel-powered models than with shock heating. And it's a simple physical reason why. The nickel-powered models, you're going to have the nickel even if I mix out the nickel, there's going to be quite a bit of nickel in the center. And it's still powering the light curves to late times. If I was shock heating, I'm heating out the outside. So it heats it on the outside and then falls off quicker. So right now, the models that are the shock heating ones are the blue, or I don't know, green, blue, whatever that color is, triangles and triangles. Those are all shock heating or nickel plus shock heating. So they're a combination of shock heating plus nickel. They are all my quicker fall off times. If it's only nickel powered for these supernova, I would get something that takes longer to fall off. The time for the light curve to drop would be longer. So at least with these calculations, the shock heated models are a better fit to the data. The trend is right. The only thing that I would say you should always caveat anything we're saying is remember the plot that I showed you at the beginning where we did the code comparisons. And the codes, especially at late times, got answers that were many orders of magnitude different from each other. So it could be with a different implementation of the atomic physics, a different implementation of the transport scheme, you could get different, a different answer could be right. But it certainly is true that if you have shock heating dominated, you can rise at the same rate, but you will fall off at a quicker rate. So these are kind of trends that we're looking at. This is where we need a lot more study to figure this out, but this will give us an idea of how much nickel do you need to produce in your supernova to explain the light curves that we're seeing. You don't want it to be nickel powered anyway, dominant in these 1Cs, because then you're going to have to work really hard to make a lot more nickel than you typically produce. So they're getting results of 0.4 solar masses of nickel, so that's hard to do. I think when you add shock heating to it, you can explain these with 0.1 solar masses of nickel or something like this. So the answers getting this right will tell you how much nickel has to come out of your supernova. So this is one of the things that we are trying to understand for the light curves. The other thing that we're working on a lot on is the shock breakout, and we already had some discussion from David Vartanyan's talk on this. But there's a set of models. So the simple ones, and I encourage you, if you ever want to learn about shock breakout, Waxman and Katz have a nice review on this where you can see how the models are working. People have started adding things like what happens if the explosion is asymmetric and you get different different explosions at different times. Chris Irwin in 2021 did a nice analytic study of asymmetric shock breakout, and how does the light curve depend on the asymmetries. And we saw David's talk. There's groups studying the asymmetries in the convection of stars, and that's also changing what we're doing. The thing that we're learning with shock breakout is it's more complex than you would think it is. So like if you really want to do it, you have to include your asymmetries in your star. So this is from the Metsukapa's group. There's their little star. I then take their explosion and make that red line. So I've taken I've simplified it to my little red line. And I have it in there. It's exploding, and then it's exploding into this convective mess that is the hydrogen envelope. I have to include that physics too, so that's going to make a difference. And there was some nice work by Lars Bilston's group at Goldberg has a really nice paper where they're studying that hydrogen envelope. We need to have that done right if we're going to do shock breakout. Then we also need to worry about the circumstellar medium and model that right. So there's all this physics that you want to do right. And I'm going to spend the last bit of my talk just showing you some of the details as we started to model this that I realized made this a problem that I should never have gotten into. And I blame the other light curve people for leading me astray and making me think that this would be easier than the engine community. So step one was simple shock breakout. So if I have this model, these are the different colored curves are as a function of time. So I have this blast wave that's moving out. It's a nice simple curve. You see this in 1D all the time, where I have a nice simple curve. It's decelerating as it's going. This is going through a stellar wind, so it's R minus 2, so 2 less than 3, so it's going to decelerate in from the set-off solution. So it's decelerating. It's all great, and then the photons start to lead the shock. And the simple shock breakout model is the photons are trapped. The photons are free. You're good. That's not what happens. What happens is the photons start to lead the shock. And we see this in experiment, by the way. So the photons lead the shock. They then interact with the material above the shock, and they accelerate it. They deposit energy and momentum and accelerate it. So what you end up getting is this mess, is the brown, the gray, and the red curves are, with time, that the radiation is accelerating the wind. And so when you look at this, when you look at a shock, this wind material is getting accelerated by this not quite optically thin, not quite optically thick radiation flow. And so this is the kind of physics that we're now trying to model better. And so unfortunately, it's not just are you doing, so in this case, these models are discrete ordinate, so SN method. I think it's S8 for this model. I'm doing the transport. It's not just am I doing higher order transport, doing the transport all well. It's also how well am I resolving this. All of that physics has to be done right to get this done. But this was just a simple r to the minus 2 wind. We can also do other models where I take on the left plot there is my simple initial condition. Again, I wanted to do just a simple shell, see how I model it. I have the supernova blast wave hit it. So it's hitting the shell. It shock heats, so I get that shock heating. And this one's nice and clean. But if you look in the density profile, the middle plot, and you zoom in, you see that it's already getting turbulent. And that's going to make things harder for me as well. So even when I do a simple model, the turbulence can get developed. And here, again, I'm doing a simple spherical explosion. This is me going one step harder than the just doing r minus 2. And already it's getting messy. The good news is the temperature of that shock is what we would expect from just a strong shock solution with a little bit of an efficiency parameter put in. So I think the analytics tells us that the physics is doing what we think it will do. We could probably come up with a recipe to put into our light curve codes to model this physics. The next step is if I add instead a density parameter, density profile that's clumpy, and then ask, what do I get if I do that? And so this is the initial condition. I have these clumps put in there. It was in a wind that was driven by lines. It had weird features. The star was blowing things off. I'm mimicking that with a clumpy medium. I then run a supernova shock through it, and this is the mess that it makes that we're now trying to understand is how does this model actually, how do we get explosions from this kind of model? And so this is where we're at right now on this, is how do we get this physics modeled well? Here, I don't see how you get around doing this with anything but a higher order transport scheme, Monte Carlo, SN, maybe higher order PN. Corey Hawk at Oak Ridge has a method to use an M4 model that might solve this. I know I'm just saying words for those of you that don't do transport, but these are different higher order ways of doing higher order schemes for the transport. But this is the kind of physics that we're trying to understand to incorporate this into our light curve codes so that we can model it. The goal that I have for this is we study this physics, understand it, and then make a recipe that we can put into the light curve codes that are typically used so that we can do it. Because the light curve codes then have to do all the atomic physics really well. Like Luc Desart is doing this complex full rate equation for the level states of the atoms to do his light curves well. He's not going to do that in 3D rad hydro. He's going to take a recipe that we can produce for him to do the shocking. He has a recipe now. Hopefully we can do better recipes with using these models to guide it. But we're not just limiting ourselves to trusting our codes to do this. We can also set up some laboratory experiments. So this is a picture of a laboratory experiment we have. So on the left, it's a gold hohlraum. So it's a cavity that's lined with gold that we then shoot lasers at, heat up the cavity. The cavity then drives a radiative shock through a target that we put on top. So there's a hole in this hohlraum that we're heating up the hohlraum and then letting a shock go through it. We can get the hohlraum up to, at the National Ignition Facility in Livermore, we can get up to about 100, 150 EV. We may have a trick to get up to like 400 EV. Just to play, so we're getting closer and closer to supernova conditions. The way we're going to do that is we're actually causing a little thermonuclear explosion. We're going to, this inertial confinement fusion, you have a pit that you compress and then it actually causes fusion. So we're going to cause the fusion. That fusion is going to drive a blast wave for us instead of just hot material. And we'll run it through our targets. And so then we made a target where we put in clumps into the target. So you can see some of those clumps on the left, which is the density profile. This is after some time. The middle is a temperature. What it is we're doing, I think this was a 76 group radiation transport scheme that I then get the effective temperature for. So that's the effective temperature for that model. And then the right is the composition. We do that experiment. So this experiment is about 1 centimeter in size. We then shine X-rays on it and get a spectrum, and that lets us get some information about the temperature profile. And what it's really telling us is something about these clumps get heated and they expand, and that reaction that we need for our clumpy medium and our supernova is what we're studying. So we use these experiments to study it. Somehow I convinced them. There was a telescope proposal called MoonCat to observe X-rays from supernova. The proposal never got in because NASA canceled that call this year. But I did convince them to change the name of the experiment. So this is called the MoonCat experiment. I think they didn't realize why I was listing MoonCat, but that's where we go. So we are doing these experiments to try to compare to what we hope will be good data from astrophysics in the next few decades. So the trick with this, I think a lot of these kind of electromagnetic calculations is it's not, again, just like the nuclear physics, it's not just we do calculations, get an answer. We do laboratory experiments, we model those laboratory experiments, and we have a lot of work going into there. That improves our models, how we're doing the rad hydro. We then apply them to astrophysical events. We model the astrophysical events, compare them to observations, and this is going to be an iterative process where you're going back and forth between the models of the experiments and the models, and then the astrophysical events and the observations. And so we'll have this kind of iterative process where it's all combined. What makes me excited about this is really, we've gotten to a point in astrophysics where we actually need to do better than the simple back-of-the-envelope physics or the simple radiative transfer models. And this is a way to really tie in this physics and engineering community to really study things. Just for fun, on the bottom there, for those of you that don't remember the early days of commodity computing, they were called Beowulf clusters, and they truly were commodity computers. These were little desktop machines that were for office work. They were called shuttle boxes, and this was in 2000, we were able to get a machine that was number 74 on the top 500 list, just based on commodity pieces. And this was called the Space Simulator. It was the design of Mike Warren, one of the innovators of what is now commodity computing. But it requires this whole mix of experimentalists, computer experts, mathematicians to come up with better algorithms, then tying together with all the astrophysics. But with all of this, I think we will get better and better models and be able to solve this. So I want to leave with the astrophysics community realizes that they need to work all together to do this. And they've been having a set of time domain and multi-messenger meetings. The first one focused on what are the science problems that we think are time domain and multi-messenger. The second one was on what are the instrumentation detector development that we have to do time domain and multi-messenger astronomy. The third one really was on the modeling. And that's where we discussed a lot of these physics. So a lot of what I was talking about today came from this, what is the physics that we need to do and what other physics communities do we need to tie to? There's a fourth one coming up in October of this year. It's going to be on the electromagnetic follow-up. And so this is where if you have requirements for the electromagnetic follow-up, and I'm looking at my friend here, this is what we need. Feedback on that would be useful. Their plan is to get the electromagnetic community to work together and say, you get a gravitational wave event. These are the observatories that will be on it, and at what times do they have to be on it? Because right now what we do is we fight for time, right? We try to get JWST, can we get time for this and all this stuff? We're going to have it so there's a set plan ready for when an event happens. It would be good to have that same set plan for supernova, a galactic supernova. So if you're interested, that meeting's coming up, and please attend. And I'll just end with, we have a lot of these follow-up observations that we can do. There's a lot of electromagnetic studies we can be doing. There's a lot of ways to interact. We actually have this slide that I show you on the constraints of the supernova engine. We're trying to build a community that will actually do, you can add and say, oh, what about this diagnostic? What about this diagnostic? How do we make it so that we have a complete list of the diagnostics we want to use and what we need to do on that? There's a GitHub webpage where you can add things that you think we should include when we're having discussions, when we're going to NASA and saying this is what we need. When we go to the ground-based telescopes, what do we need? So I encourage you to get that QR code and go add anything that is missing from the current study on this. And with that, I'll end my talk.
Thank you very much. We have time for questions.
Chris, thank you for your wonderful comprehensive overview of what can be done for or should be done for the electromagnetic sector. I have a question for you with respect to, I would have many questions, but they are more on the details. This is parametrically varied conditions. Sometimes you had some numbers which didn't really tell the non-expert of the paper what exactly was a reference point. And in this respect, I have a question for the rates you gave. You said that the fraction of the jet-driven supernova is 5%. 5% of what? Of the observed supernova distribution or of the real population?
It's 5% of the observed in ZTF. So it's even ZTF specific. So this is, it's 5, so in ZTF, roughly three quarters are 1As, 1/4 type 2s. We know that there's more type 2s than that in general, but the 1As are brighter, so they get more. So it's in an observed sample, ZTF only.
And when you convert that to a real population, what would be the number? 1%?
Yeah, that's a, so I don't think, like Dan Perley did not publish what does he think the biases are. So
Yeah.
that's, I mean,
Yeah.
there is work to do there. It's not clear to me because there's, so I don't know if it's smaller or bigger even. So that's my problem is I don't know what, certainly those are brighter. So your first guess
biased.
is the
You're-
right thing
you're
to do
biased,
is that there's actually less.
Yeah.
But there's also, there's also the transient observer bias where they see something weird, they focus more on it. But the other one is these broadline ones are harder to prove. So sometimes you can underestimate it. I don't know if it's I don't think I would bet more than 5 plus or minus 5% is what I would say on that. But you know, it's not completely zero. So 5 plus or minus 4 maybe. But I think you know it's going to be a small fraction. And my thing is, can we be missing these jet-driven explosions in models that just don't have broad lines? I am not convinced we're missing many. So I'm not convinced that there's a jet-driven, I'm not convinced that the jet jitter mechanism is going to be a way to make lots of supernova be jets. I think it is on this small, you know, less than 10% fraction. And I wouldn't be surprised if it's 1%.
Thanks.
Yeah, thanks for the nice talk. I wanted to ask you about the asymmetries that you mentioned. So one of the things that that we have with gravitational wave signals is that we can try to measure if there is rotation, but we always have the problem of the inclination angle, which we don't unless we know the inclination angle with respect to us, it's very difficult to put constraints on whether we have rotation or not, just from the gravitational wave perspective. Are there any prospects from asymmetries to get inclination angle of the angular momentum of the system or something like that?
So if you do assume that it's a jet-driven explosion, right? Then and the jet is off, you know, so the rotation, the axis is like this, and I'm observing straight above, then we will see that in the spectra. So if that's the dominant observation, we can get evidence of that in the broad line. You know, so when they look at these broadline supernova, good enough data will let us extract. We're not going to be that accurate on the inclination, but we will be able to say it's not face on, it's off. And depending on how good the spectra is, we can probably use that to get an idea. We did this in the gamma rays with 87A. We could see that it was, you know, it was an explosion that was going in one direction and not pointed at us, in fact, pointed away from us at an angle. So you can, with that data, get that, especially nearby supernova. If you know, okay, so my dream with gamma ray detectors, COSI's going up. It's going to be okay, but it's a typical gamma ray detector that tries to do everything. You could design, if we came up with the argument, we could design a gamma ray mission that is fairly narrow field of view that you would point at an observation, but can go far out, you know, out to the Virgo cluster. And so one of the arguments for what we should do, so one of my hats is I'm the co-chair of the Future Innovation for Gamma Ray Science Analysis Group for the US on what are they going to do for gamma ray detectors. One of the things that I think is the right argument is we want a focused instrument that points in one direction, you know, a very narrow field of view, but can go very deep and measure these line profiles. And that would give us an idea of what is, if it's a jet-like structure or even just an asymmetric supernova with one or two lobes going in one direction. So you get this sloshing, and if you explode in, there's really dominant nickel in one direction. If we did this gamma ray emission that can do that, and observe it out to the Virgo cluster, then I think we would be in a good position. We need to make that case. So this is the right community to say, if we did this, this would help us. then I could go to the gamma ray community and say, this should be what you do. Don't observe the stupid AGNs. Go do our stuff. So, but unfortunately, that's where we're at. We're not going to be able to get every gamma ray mission, that we want. We're going to have to pick and choose what's going to happen in the next 30 years, and that may. There will definitely be a wide field gamma ray mission to observe gamma ray bursts, but it's cheap. It's probably, you can do that with a very small amount of money. It would be expensive to build this kind of focused mission, but it could be the right science to do. And if we could argue that, then that would be what they'd build.
Okay. And if it is not broad line, I mean, I understand in this case if you have a jet, but if in a regular supernova, just from asymmetries, can you get something?
You can still see this. So we do this with 87A. We're looking at it and looking at the line features, and that gives us a prediction of what's the nickel distribution and what's the asymmetries. It's hard, but you can look at these velocities and then get an estimate. So that would be the way you do it. So even a normal supernova, we could look at the asymmetries. Not just with the broad line.
Thank you.
Okay, yes, one more question.
Thank you. Chris, could you go to the slide with the nebulous 2025 light curves that showed nickel mixing?
Yeah.
And while you're doing that, do you know why in the Blondin 2022 paper, SNEC wasn't included as one of the codes to do the light curve?
Oh, you mean in the comparison?
Yeah.
That was just whoever went to the, oops,
Gotcha.
I've gone past it, huh? That was just whoever went to that, to the meeting. So the groups that are there are, you can see the codes. It's Artis, it's CMFDen, Sedona, Stella, Summa, Supernu, Tardis, and Eurolite. These are all different transport mechanisms. So Supernova is Monte Carlo with discrete diffusion, Monte Carlo for the optically thick part. There are ones that are SN transport. There's several of these are Monte Carlo. There's variable Eddington factor. I suspect all of them would lie in, I think a lot of the mechanisms would lie within this range of transport schemes. They're using everything for the way they implement the opacities, different expansion opacity mechanisms, there's groups there that just use a line binning mechanisms. There's a set in the community that, and I would argue they know their physics less, where they think it's obvious what mechanism you should use to do to implement the opacities. It's actually really difficult to figure out what you should do. And almost all of the mechanisms have things that make them bad and make them good. I can show, we have test problems where we can show using an expansion opacity is actually getting the wrong answer. But there's, and so we do lots of comparisons of how do you implement the opacities, especially we have home meetings on this for Kilonova, where we study that. But this is the kind of range of answers you get. I suspect SNEC would lie in this range.
Thank you. I'm also more curious about the nebula 25 results, where you show the heavy nickel mixing.
Yeah.
Curious, under what ranges of physical parameters is this possible? Because this is something I'm very interested about. Nickel decay for around a few percent of a solar mass will give you intel around a few times 10 to the 48 ergs over months. And here you're saying over 10 to the 42 ergs in addition at breakout. And I'm guessing these are red supergiant models. And yeah.
So all of these start with something that's hot. These are 1Cs, by the way.
Okay.
All these are starting with something that's hot. So part of the light curve is just because it was shock heated at the beginning. But then you're adding the nickel, the variations you're seeing. Which one of these did? Okay, unfortunately, I did not include the plots where we varied the nickel mass. These all have the same nickel mass in all of them. So yeah, sadly, you can vary the nickel mass, and I could show you offline where we just zeroed the nickel mass and did a simple model. But that one would go up and come down quite quickly. Especially the late time evolution, the nickel deposition is pretty critical for these models.
Okay, thank you.
And these are all 0.2 solar masses of nickel.
All right, let's thank Chris again.